All right, everybody, welcome. It's Tuesday night, and we're back here to do some chemistry. And tonight we're going to just do some different topics, kind of general chem, organic chem, a lot of overlap there. So say hello in the chat. I can see there's a couple of us here already. Just check in so I know who's out there, hopefully some familiar faces. I wanted to start by showing you an image here. This is, you might have saw this when we were starting. This is an image that I created, and I used Midjourney to create this image here. So I'm going to jump over to another screen where I have it larger. And at first, this looks like a pretty cool chemistry image, right? You're looking at this thinking, yeah, that looks normal. But there's a bunch of stuff wrong with it. And this is what these AI image generators kind of do weird stuff. So take a quick look, see if you can see 2 or 3 things that just don't make sense. There's one big thing that makes absolutely no sense. So why don't we start with the big thing that makes no sense? And I see Anna's here. Hello, Anna. Fab Insanity, Florida. Awesome. That's I like that that username as well. So the big thing that I see here that's really kind of weird is you see how this is bolted into the wall here. There's no way that can be behind the bolted thing into the wall. And so when you're looking at these AI images, you'll see this a lot now where people will have these images and things like, how could glassware be behind the wall? That makes no sense. And how can these test tubes just kind of be standing up on their own? That also makes no sense. I don't know, maybe this is some kind of pharmaceutical, I'm not sure, but here we have boiling and I can see that, but they're like on fire. So anyways, when you see these AI images, look at them real close because lots of times they just don't make any sense. All right, I see Guia Cameras here from Brazil. Awesome. And Realms. Nice, nice. Caesar, you're here. Caesar Santiago. Excellent. And so as we go through, ask questions. Caesar, I see you were you have some things you might want ask questions about. As we go through, ask questions and let me know how we're doing. Let's start with resonance. So we see resonance quite often when you're taking general chemistry or organic chemistry. It's really important. In organic chemistry, it helps you tell whether the molecule is going to be stable, how strong of an acid or a base it might be. So real important in both general and organic chem. So here's how it works. If I draw the Lewis structure here, I could put the double bond here, but I could also put a double bond here and make this a single bond. That would be okay. It would still be a valid Lewis structure. I could also put the double bond here and make this a single bond. So there's like 3 ways I could draw this. And that's the problem with Lewis structures, is that they're kind of like a snapshot. In reality, the molecule, it's going to be all those ways combined, averaged out. So the negative charge here, it's spread out on the oxygens here. And so when we talk about resonance, it's kind of like we take the valid Lewis structures and we average them to make kind of a hybrid structure. And this is what it's really like if you were to be able to see it in real life. So what you'll see in textbooks is this image right here. And this is what you need to know. What do these arrows mean? So if you have any idea what these arrows mean, drop that in the chat. So these are equivalent resonance structures. You can see the double bond is in a different place. So they're exactly the same except the double bond, it's in a different place. So the resonance structure, this here, it just means that these are all averaged. You can't think of these as switching back and forth. They're not changing back and forth. They're actually the same thing here. They're just an average. So that's a huge idea in resonance. All right, so see if you can do one of these resonance structures here. Oh, my thing is frozen. That's not good. Okay, well, we have a bit of a technical problem here. I'm not quite sure what to say about this. I think I'm going to restart this, and while I'm restarting it, if you have any questions, drop them into the chat while I try to figure out what's going on here. Maybe that'll make it work. Nope, we're going to have to close it and start it. Oh, let's close that. Inkscape's a really neat program. It's actually available. It's a free program, and I use it for all my videos. So it's really nice. But like any program, sometimes it kind of freaks out. Here we are. Okay, so see if you can figure out what the 3 resonance structures would look like for the carbonate ion. That'd be a good exam question. What are the 3 resonance structures? So I'm seeing not seeing much on the chat. If someone could post a chat message, I'd feel like more like we're here. So Realms, you said hello. Someone else say hello so I know it's working. All right. Okay, well there's Pavel. Excellent. So you're saying that we could switch this double bond around. And yeah, that's the idea, is that we could put it here, we could put it here. So there'd be 3 resonance structures. But what about this 2-? Hello, Lilac and Lola. Excellent, great. And Anna, College Junior. All right, almost out there. There's Loretta. So you guys are there. You're just either paying close attention or quiet tonight. Fluffy Lavender. Hello. All right, so the negative charge. Somehow we have to figure out where the negative charge is. And since these are more electronegative, that 2-, it's spread all over these oxygens here. So let's see if we got it. Yeah, here it is. And since it's spread over the oxygen, each one of the bonds is has a 2/3 negative charge. And this is what the carbonate ion would look like. And on those oxygens, we'd have 2/3 negative charge kind of delocalized over it. And then Pavel, like you were saying, we'd have 3 structures here, and they're not switching back and forth. It's just showing that they're an average, and that's a huge idea. Realms, you asked when you'll encounter resonance in chemistry. You usually do it when you're doing Lewis structures. That's about the time that you'll see it. But it's pretty much every general chemistry class does resonance, and then organic chemistry, they do resonance all the time. It's a big idea with organic, so important to know how that's working. Hello, Huzifa. Where am I from? I'm just from right outside of Washington, D.C. in the United States. So about 10 miles, I could ride my bike there pretty easily to the White House, and they wouldn't let me in, but I could do it. Pavel, why is it important? Because resonance tells you about stability. So when you have resonance, you usually have a more stable molecule, and it can affect reactivity. You can have it affect, you can tell a lot about resonance, about acid-base chemistry based on resonance. So lots going on with that there. All right, so we're going to leave resonance here, but to do resonance, you've got to be able to draw a Lewis structure. So take a moment and just see if you can draw the Lewis structure for boron trifluoride. And I'm going to give you this here. This shows you how many valence electrons you have. Not when it's upside down. Valence electrons. So here, all these have 1 valence electron, 2, skip the transition metal, 3, 4, 5, 6, 7, and 8, except helium, it only has 2 valence electrons. So draw that Lewis structure, give it a try. Kashmir, awesome, in India. Boron is an exception to the octet rule. Yeah, boron is right here, and you'll see it has 3 valence electrons. And then fluorine right here has 7. So yeah, it is an exception. Lucia, when we're talking about resonance in ozone ends up, I'll draw it right here for now, has a single bond and then it has a double bond. So you could put the double bond here, or you could put it over here. So both of those are valid Lewis structures. But in reality, it's more like it's average, so you have a 1.5 bond between these two because it's symmetrical. So I hope that kind of helps. Well, lots of folks are in chat. You're like, all right, thank you, Hazifa. Akil plays, hello, and Kyle's there from Canada. I live in the U.S. and I've never been to Canada. I have to go there one time. Hey, Raja, Caesar, you're that. Yeah, we do have a problem with the ozone hole. Even though I said that resonance stabilizes the molecule, O3 can be broken down by different substances like chlorofluorohydrocarbons and UV light. The weird thing is that ozone around the Earth is important. It blocks UV light. But ozone on the ground, it's produced by certain engines and the production of energy. It's a pollutant on the ground. So good and bad. Be is also an exception because beryllium, right? If you look at beryllium, it's 1s2, 2s2. So it could easily lose these two to have a full outer shell here. All right. Hey, Kyle, good to hear you passed your exam. So let's do boron trifluoride. So first thing you do with Lewis structures, add up the valence electrons. So for boron, we have 3, and we have 3 fluorines. Each one is 7. So we get 21 plus 4 is 24 total valence electrons. So you always put from Ghana. Awesome. I actually lived in Ghana for 2.5 years in Boku. Up next to Bolgatanga and Tamale area. So 24 valence electrons. Boron, it's over, whereas boron is here. Fluorine's very electronegative. So you always put the least electronegative in the center. Fluorine, there on the outside. And then we have 24 valence electrons. So right there, I'm forming chemical bonds. I've used 6. Then I do the outside. And I want to give each one 8 so that it has an octet. Do it over here again. And when I'm done, if you count up all the electrons, all have used 24 valence electrons. And like I think Pavel was saying, we only have 6. So boron is actually one of the exceptions. And if you look in the description of this chat, there's a link to all about the different exceptions, including Be. So boron is okay with 6. And that's our Lewis structure. So I hope that helps you think about Lewis structures. The octet rule works really well for these right here. But after that, things can get kind of weird. You can have, these down here can have more than 8. Can get kind of weird there. All right. Fab, resonance is a huge thing in organic chemistry when you're determining the reactivity of molecules. Yeah. I probably won't speak to that much tonight, but you get involved in organic chemistry of pushing electrons around in a molecule to look at the different resonance structures. And then there's a set of rules to tell what's going to be more stable and what's going to be more acidic and basic. And you spend a lot of time on this in organic chemistry. And if you know that, then you can do your reaction mechanisms. So that's why it's important. All right. Let's go down here. So that's our Lewis structure. So now, let me copy our Lewis structure here. One of the things we do is we use Lewis structures. We draw our Lewis structures. One thing is for molecular geometry, but another is to calculate the formal charges. So here's our Lewis structure. See if you can figure out the formal charges, say, on the boron. This is another organic chemistry thing. They do it in general chemistry a lot to make sure you drew the Lewis structure right, but in organic they do it a lot as well. So my current time here, Huzifa, is it's about 8:44 p.m. It is night here. It is morning for you. Aki plays. I love Lewis structures. I have like 500 videos literally on Lewis structures. If there's a Lewis structure I haven't done, I would be surprised. All right. Hello, Bruno. All right. So let's figure out some some resonance, and then I'll show you a trick for you organic chemists how to figure it out for the molecules you use most of the time. So let's look at boron. You count the valence electrons, and those are the ones around it. So boron, I'm sorry, that's where you get from the periodic table. So we actually need to go to our periodic table here. Let's just take it down here. And we'll put it over here so we can see it. There we go. So boron only has 3. So it has 3 valence electrons, non-bonding electrons. They're the ones that aren't in bond. So all of these between, those are chemical bonds. But everything out here, these aren't bonding. So we have 2, 4, 6 non-bonding. Oh, I'm sorry. These are non-bonding. There are none. All of these are in chemical bonds. So we have 0. And it's the 6. It's the 6 of them that are in the bonds. 6 over 2. So 3 minus 0 minus 3 is 0. So you'd write 0 for the formal charge there. So try to do the fluorine. Fluorine is 7. It's got 2 bonding and 1, 2, 3, 4, 5, 6 non-bonding. See if you can figure out the formal charge on the fluorine. Hello, Amna from Indonesia. Nice. Yep, you got it, Pavel. That's the 0 there. I have a bunch of realms. I have a bunch of videos on oxidation numbers. In the description for this video is, we'll do oxidation numbers in a minute. In the description for this video, there's a real good video on just doing oxidation numbers for any compound, element, or ion. So you might want to check that out. All right, let's do this. Fluorine, 7 valence electrons. It's in group 17, sometimes called 7A. Non-bonding, 2, 4, 6. Bonding, 1, 2. And we put that over 2. So it is actually 7 minus 6. All of these are going to be 0 as well. So some teachers give you a little different formula, but you'll always, it's the same thing. So those are formal charges. We use those to figure out if our Lewis structure is well. So if there's 0, that's good. That's what we want, is to have it as close to 0 as possible. Oh, let me put this in the, this is a guide I wrote about formal charges. So you can get that. It's available to members, but let's just put it here so you might find that useful. All right. So can you figure out the formal charges on, the elements here? And here's the deal. When you're finding formal charge, all of the formal charges on the atoms need to add up the charge on an ion. Formal charge is a measure of stability, but it's also kind of a measure of which Lewis structure is more favorable or likely, which is related, to stability. If it's not stable, it's going to not really exist. So I would agree it's a measure of stability as well. All right, so we could do our formula again. Let's do our formula just for this oxygen. We said we take valence electrons. Oxygen's in group 16, so 6 minus the non-bonding. Is that right? Non-bonding electrons. There are just 2. Minus the bonding. Nope, I'm sorry. Non-bonding, there are 6. 2, 4, 6. Minus the bonding over 2. So you get -1 for this oxygen. And you write it like that with parentheses. And then since this is the same, you get -1. So this is a good skill to have, especially for general chemistry. But what you'll learn as you go on in chemistry is whenever oxygen has a single bond, it'll be -1. Whenever it has a double bond, it'll be 0. So if you memorize that with a single bond, this oxygen's a -1 formal charge. With a double bond, it's 0. You can go really fast on exams. You don't have to go through all that formula up there. And since everything equals 2 minus, we look at that carbon, what's the carbon have to be? 0 plus 0, 0 plus 0, plus -1 plus -1, that would equal 2 minus. So you can figure the carbon out that way. So for you organic chemists, here's kind of the rubric, and that's in the link I put there for the guide here. If you memorize, I would just memorize these right here. It'll save you so much time. So see if you can use these to find the formal charges here. And while you're doing that, I'm going to jump over, check this. No. All right. So, let's just look at the carbons first. 4 bonds, formal charge is 0. 1, 2, 3, 4, 1, 2, 3, 4. So each of these carbons has a formal charge of 0. Hydrogen only forms 1 bond, so all the hydrogens are 0 here as well. So hydrogen, when it just has that single bond, it's going to be 0. The oxygen, though, we have 2 bonds and 2 lone pairs. So 2 bonds, 2 lone pairs, that's also going to be 0. So everything I chose tonight is 0, but that's not always the case. All right, so if you need this chart, it's actually in the link that I put in the chat a little bit ago. And I did not know this when I took organic chemistry for some reason, and I wish I had. It made life a lot easier. Hey, no problem, Wong Tong. Wong Tong Gong Bong. Wow, okay. Yeah. So take a look at this again, and we're going to try to do one without the chart here. Big thing to remember is oxygen with 2 bonds, that's the 0. 1 bond, 3 lone pairs, that's -1. Try propionic acid. See if you can do that. All right. So let's do the easiest one first. Hydrogen, 1 bond. And each of these bonds here is a pair of electrons. So you could think of it as a pair of electrons for each one of these straight lines here. These are going to be the hard ones. So we know hydrogen with 1 bond is 0. Carbon with 4 bonds, 1, 2, 3, 4. Those are going to be 0. And double bonds count for 2 bonds. This carbon here has 1, 2, 3, 4, so it's 0. All are neutral. Hey, absolute 0, good to see you there. Emma, what is the single bond structure for methane? Methane is just like this. See, carbon will form 4 bonds. So here's 1, 2, 3, 4. So that's CH4 methane. So here our carbons are all 0. But the trick to getting the oxygen here is you see 1, 2. We know oxygen's going to have an octet, so it needs to have these lone pairs here. 2, 4, 6, 8. Down here, 2, 4, 6, 8. So often they won't draw them in. They expect you to know that those lone pairs are going to be there. So double bond is 0. Down here, we have 1, 2 bonds and 2 lone pairs. So it's really the same, 0. So like absolute 0 said, everything here is going to be 0. But watch out for these extra electrons that they don't show you. SO4, you're going to have to search on Dr. B SO4 for that one. And I have a video on that. It's gotten a lot of views. I don't know if it's 1 million views yet, but it's pretty big. All right. So we did this formal charge stuff. So formal charge is very different than oxidation numbers. So when we look at formal charge, we're saying everything's covalent and all the electrons are shared equally. But when we look at oxidation numbers, we're saying that the more electronegative element gets the electrons. So we use oxidation numbers with redox, where electrons are transferred in reactions. Becomes important for us to track those. I have a big section on redox if you go to breslin.org. That's my website. If you need help with that, I can't even spell my name, breslyn.org. That's my website if you need redox. So let's do the oxidation numbers here. These are the rules, and that's what makes oxidation kind of good and bad. There are a lot of rules, but if you know the rules, it's pretty easy, right? You just follow rules. So let's follow some rules. Free elements. That would be something like Na or Fe or H2, just one type. We don't have that. And we don't have ions because there's no negative or positive, so it's not an ion. But it is a neutral compound. So we know that everything's going to add up to 0. And we know that fluorine is always -1. So fluorine's -1. In this case, it doesn't really tell us about boron. But if everything has to equal 0, 3 times -1 is -3. So we have to have a +3. So our oxidation number here is +3. So you kind of can figure it out that way using the rules. And note that the charge, but the symbol goes in front of the number. If you had an ion like SO4, it would go after. So you can tell it's oxidation because the plus is in front of the numbers. All right, let's have you try one. Do I have the rules down here for you? We need the rules. See if you can find out the Mn in KMnO4. Kind of throwing you off the deep end here, right into it. All right. Agent Stark, what does CH2N2 do? I guess it depends on what environment you put it in. Looks like it, I really don't know that molecule so well, to be honest. I guess it would probably be a base. It's an organic compound. So Pavel, I'm not sure what you mean by the formal charges for more. Formal charges are for covalent compounds, absolutely. But you can use oxidation numbers with covalent compounds too. You do quite often. But formal charge is almost exclusively for molecular compounds, 2 nonmetals or more. A+ in general chemistry, Ahmed, that's good because I don't think I got A+ in general chemistry, so I'm glad someone did. You're right, Absolute Zero. I did a poll. We should look at that poll just today on the permanganate part. We'll look at that in a minute and see. So here's how I would figure this out. Potassium is in group 1 on the periodic table. So I know that group 1, all of those are +1. And I know that oxygen is -2. And I have 4 of them. But manganese, that's a transition metal, so I have no idea what that is. I'm just going to call that X. So I could say +1 plus X, 4 times -2 is -8, equals 0, because it's neutral. And then X minus 7 equals 0. And like Pavel was telling us, X equals +7. So that's a good way to figure that out. You might not need to do all this. You might just be able to look at it. So let's give this one a try. We'll move our stuff down again here. And here the trick is that it's kind of like we did before, but this is an ion because of this negative here. So everything has to add up to the charge on the ion. So see if you can figure out what the manganese is in this ion here. Give you a second to do that. And I did a poll on this, so let's see, we can compare how you did to everybody in the poll. Thank you for reminding me that, Absolute Zero. I like the permanganate ion. Yeah, 1.2 thousand people have done the poll so far. 80% got it right. That's like a B minus. Okay. Physical chemistry is difficult, Agent Stark. And what I recommend is that you work a lot of problems. There's something called, when I took physical chem, it's a SCHAUMS, Schwamm's Guide, and it has just worked problems. And I would just go and work problem after problem. And that's what got me through physical chemistry, because it's hard. Absolute Zero, you are right, and Pavel, you are right. Let's do this one here, and then we'll see, and then I'll show you the poll. So in this case, move over here. Yeah, Schwamm's guides, those there, I'm sure they're still making them. Those were just really, really helpful. So everything has to equal -1. So we know that this is -2 times 4. So that's -8, and we just call this x. So if we add 8 to both sides, that would give us +8 to both sides. That would give us +7. So it's the same. And if you think about it, when you put that K plus here, right? These here, I don't know what just happened. Something happened. We're in outer space. At any rate, when you put that K plus on there, I'll just write it here. Oh, I can see it there. I can see it. It's very small. Sometimes when I'm making videos, stuff like this will happen, and then I have to stop in the middle of the video and start over. So you can see that the plus and the minus will balance out. That's why KMNO4 is a neutral molecule. Let's look at the poll. Let's see how people did on the poll here. So I asked, what is the oxidation number of the manganese in this permanganate ion here? And 80% of the people got it right. So I guess that's okay. I think a lot of people do these pretty quick. If you go to my community tab, so if you go to my channel, just up W. Breslin, and you go to community, I post these questions every few days, so they're kind of fun. All right, what time do we have here? Yeah, do a little bit more, and then maybe call it good. Yeah, let's look at the molecular geometry of two molecules, because I really like molecular geometry. For some reason, that is attractive to me, kind of such a visual thing. So if we have, remember our Lewis structure looked like this. Here, we didn't have any lone pairs because boron's an exception to the octet rule. If these all spread out equally away from each other, what would that look like? Kind of reason it out down here. We have 1, 2, 3 things. Thank you, Litter44. 3 things are attached, right? So that makes it a steric number of 3, no lone pairs. It should be trigonal planar, so it should be all spread out. Let me go back to that, Pavel. Remind me if I don't. That's a good question of why it's an exception. Let's look at, if you're studying chemistry and you go to search on PHET, molecule shapes, you'll find this. I guess I could put it in the chat here too. You got it, Fab. Trigonal. I used to say trigonal when I was a student, but it's a trigonal planar. All right. Well, that's one way to say it. So if you think about it, here's our boron molecule. We're going to put 3 of the fluorines on. So 1, 2. And because these have electron clouds around them, they kind of push each other away, right? They don't want to be next to each other. Watch what happens when we put the third one. Now they all spread out, and that's your trigonal planar right there. It's kind of like all in a plane, and there's 3 of them. They're all spread out. You can see the bond angles there for that too. What do you think would happen if we put a lone pair right here? That's kind of an interesting thought. Lone pairs occupy space, and they're an electron cloud. They would push other things away, like the electron cloud around the atom. Let's try it. And you see it pushes them down. So we get this pyramidal type situation. Yep, you got it, Pavel. It's a parameter. So kind of fun. If you have a chance, play with this. You can look at different things like, let's put some more lone pairs on, and then you start getting kind of weird stuff like, what is this? T-shaped. I guess it's like a T. All right, let's go back and do a tough one. I don't know if we're going to be able to do this one in that program. So SF6, in order to do this, you have to have the Lewis structure. And absolute zero, that's right. The pyramidal would be like ammonia. Yeah, there's a lot of things that kind of go together, Fab. That it's all a lot of the stability stuff is very related to geometry and spatial considerations. So I'm going to go out and get the Lewis structure here for SF6 so we don't have to draw it. It'll probably be like, yep, there is my video. That's what I like to see. So this is a video. This is from a video I made in 2013 when I didn't quite have a full command of how to use programs like this. So what you'll notice first is we have 2, 4, 6, 8. So 2, 4, 6, 8, 10, 12 valence electrons around sulfur. So sulfur is another exception. It can be an exception to the octet rule. Sometimes it has 8, but here it has 12. And that's because it has d orbitals now. That's kind of the big discussion. So let's look at, we got 1, 2, 3, 4, 5, 6 things attached and no lone pairs. Steric number is 6, no lone pairs. Octahedral, like absolute zero is telling us there. So let's build this because it's kind of an interesting looking molecule. So we can close out all of that, and we're going to put 6 fluorine atoms. 1, 2, there's linear. There's our trigonal planar we just had. There's our tetrahedral, like methane. This is trigonal bipyramidal. We have 1, 2, 3, 4, 5, and there is our octahedral. So that's SF6, and if you do the Lewis structure, you can start to figure these things out here. All right. I think that's probably going to be it for me here tonight. And unless you have some questions, feel free to ask some questions, and I'll be back on next Tuesday. We'll do some more stuff. Yeah, so I think I'm just going to answer a few questions for a while and call it good. Like, what's a lone pair? That's a good question. So a lone pair it's also called a non-bonding pair of electrons. And so the electrons here, so if we move this over here, the electrons between atoms, this pair of electrons, it's in a bond. It's bonded between the fluorine. They're sharing these electrons. So that's a bond. But the ones that aren't in a bond are called lone pairs or non-bonding pairs of electrons. So something like ammonia, so NH3, if we made, you're looking at me, not my screen, sorry. So these are lone pairs because they're not bonded. And then these here, they're between atoms, they're shared, so that's a bond. So thanks, Fab, I appreciate it. If we go over here and we did something like ammonia, NH3, it actually has a lone pair here. So it's just electrons, and it affects the molecular geometry as well. All right, thank you, Pavel. Why is boron an exception? So if you think about boron's got 3 electrons. It's in group 3, so it has 3 valence electrons. And it's what is its atomic number? Is it 3? Let's go back out here. Let's look at our periodic table here, if we can find it. Here it is. So here's our periodic table. And here's boron right here. It has 5 valence electrons. So if you write the electron configuration for boron, it's 1s2, so 1s1, 1s2, 2s1, 2s2, and then the p, this would be 2p1, 2p2, 2p3, so 2p1. It doesn't have a lot of electrons to share, right? It only has this energy level here, 3 valence electrons to share. So it really can't form 4 bonds. So it can't really get that octet like other things. Like when we get to carbon, carbon can form 4 bonds because of hybridization. But boron just doesn't have enough. Just like beryllium wouldn't have enough to form enough bonds to get an octet. And the hydrogen forms a duet, right? Because it's only 1s1. So another hydrogen comes along and they form the bond there. Now they both have a full outer shell. This is full with 1s2, because when you go up, after this, you have to go to a new energy level. So I hope that helps. Right, group 13 elements. Yep. It's 5. Yep, 5. You guys got it right. I don't know why I guess I was thinking it was 3 because it's in group 13 or 3. And yeah, and so if you looked at the formal charge, like Fab's saying, absolutely, the formal charge is 0. So that indicates that it's on all of the elements there. That indicates that it's really stable. So we could use formal charge to help answer that question as well. All right, Caesar, excellent. Hope to see you next week there. So boron, I don't think boron's a gas. I'm not sure. I think boron's a pretty solid, but we can always check that out. Yeah, it's a solid at room temperature. It's a metalloid. In fact, it looks kind of like this here. Yeah, like that. So that's your boron. I think all the metalloids are solid. Pretty sure of that. Yeah, and you might find this as a dust as well. So yeah, that's a good question though. The exceptions are kind of a pain. If you look at the description for this video, there's a whole video I did on exceptions that might help you out. You are most welcome, Agent Stark and Pavel out in Iowa. There, hopefully it's a little warmer than it was last time we talked. All the snow here is gone, so that's kind of nice. Okay, well, I think I'm going to call it good here, and we'll reconvene next week. If you have a chance, answer that question on the community tab. You'll get it right now, since you know the answer that manganese is +7 there in that permanganate ion. Summer. Okay, nice. All right. Good night, everybody. This is Dr. B, and as always, thanks for watching. All right, everybody. Good night, Loretta, Krika. I can't read that. Illustrious orchestrations. And yes, spiritual. I've seen Breaking Bad, so all my students ask me if I can make meth. So, all right, guys. Good night, everybody.